talk will be given by Victor Galitski from University of Maryland, and he'll speak about many body level statistics. And thanks for sharing your screen, Victor. So you can go ahead whenever you're ready.
All right, so thanks very much, Ashwin, Mike, Shamit, for organizing this virtual meeting, although I miss seeing you all in real life. So today I'll be talking about many body level statistics, and I'm really happy to see Mark Studnicki actually among the panelists, because this work was largely motivated by initial discussions with him in Santa Barbara. So since we have a pretty huge and diverse audience, I decided to spend half of my talk on an introduction to the topic, because perhaps not everybody is working on this. So, so this is my plan. So first I'll give kind of gentle introduction to classical and quantum chaos. And in particular, I'll emphasize a kind of challenge with even defining what quantum chaos means. Then I'll focus on the main kind of object of our study, which is the so-called spectral form factor. And this is actually closely related to the talk by Steve Schenker on Tuesday. And we'll see that there is a certain behavior, linear ramp in this spectral form factor is a kind of hallmark of Wigner-Dyson level statistics. And one thing that I will also emphasize here is that the standard random matrix theory, which we can also call SYK2 in modern language, can be obtained, basically read off from results of old-fashioned disordered metal theory by Altshuler and et al. So this is something which I would like to emphasize, that they're actually closely connected. Anyway, so then I'll actually talk about many body level statistics, which is a new thing. And surprisingly, we'll find that something interesting happens even in the case of integrable systems, kind of many body systems embedded into classically chaotic medium. And we'll see some interesting features such as a different type of statistics and even a level attraction. And if time allows, I'll talk about ongoing work on a field theory approach to many body quantum chaos. So, so usually when we introduce chaos, we start with the metaphor of butterfly effect, which was introduced actually in the context of climate research, where people saw that their weather simulations would produce tornadoes or not, depending on rounding off very small initial conditions comparable to the flappings of a butterfly's wings. So this is where it came from. And what it manifests is basically this phenomenon where in a chaotic system, small change in initial conditions gives rise to an exponentially large divergence of trajectories at time t. So it's a ubiquitous phenomenon, but it's actually very difficult to prove that a particular system is chaotic. So, so this is perhaps one of the first systems, billiards, so-called Bunimovich stadium billiard, which has been mathematically proven to be chaotic. So another example would be just regular metal, where instead of the external walls of a billiard, we'll have randomly positioned impurities and electrons bounce off of these impurities, and that's a chaotic system. So I would like to mention also that in physics, we oftentimes there's an equivalence in our mind between ergodicity and chaoticity, but in fact, that's not necessarily the case. It's actually not the case. In the theory of dynamical systems, there is a very rich hierarchy of ergodic systems. So I'm not going to go into details. It's not really crucial. I would like just to emphasize that there are plenty of examples of ergodic systems. That is, for instance, this irrational billiard, where you do fill up the entire phase space, but the Lyapunov exponent and Kolmogorov-Sinai entropies are zero. And then there are kind of chaotic systems of the type I care about, so-called K systems, where you do have Kolmogorov-Sinai entropy and Lyapunov exponent non-zero. So now going to quantum chaos, as I said, so it's not really easy to define it. And the main kind of obstacle is that if we associate classical chaos with the exponential divergence of trajectories in quantum mechanics, there is no notion of a trajectory. So that's a bit of a problem then. So, but there are three quote unquote definitions of what we might want to call quantum chaos. The kind of dumbest definition perhaps would be just to take a favorite classically chaotic system and just quantize it and stare at the wave functions, which are actually pretty nice. So this is one way to define a quantum chaotic system. So another kind of more meaningful way to define it is to study level statistics, the spectrum of a chaotic model. And so this definition would involve then identifying quantum chaotic systems with the presence of level repulsion. So here, what I'm plotting is the standard Wigner-Dyson level statistics, which is the kind of probability density of finding two levels with a level spacing of S. And the hallmark here is this level repulsion, that you can't find two levels coincide with each other. So, and then there is a conjecture, which is actually wrong, but in many cases it holds, in some cases it doesn't, but it's customary to introduce it, that if you do quantize a classically chaotic system, you will get necessarily Wigner-Dyson level statistics, and vice versa, that these two definitions are equivalent. It's a little more complex than that, but for most systems of interest actually does work. So I'll mention in passing also kind of new third quote unquote definition of quantum chaos, which in fact has been largely motivation for recent research, even though it's not a subject of my talk. And this is an attempt to generalize the notion of Lyapunov exponent to quantum systems. So as I mentioned, there is no notion of a trajectory. So Lyapunov exponent measures how the trajectories diverge. So, back in '68, so advisor, my late advisor, Anatoly Larkin and Yuri Ovchinnikov, so they, in the context of a very kind of, well, not simple, but rather very traditional solid state paper, they came across this type of an object, which is the commutator squared of two operators at time t, Heisenberg operators in time t and time zero. In this case, it was position and momentum. And since momentum operator is, of course, just the derivative with respect to x, so what it kind of measures is the sensitivity of where you are at time t with where you were at time zero. So this, therefore, you can say that if this correlator, which is now called out of time ordered correlator, because if you actually expand this commutator squared, you will get out of time ordered structures. So if this correlator grows exponentially, we'll call the system quantum chaotic, and the corresponding exponent, well, the quantum Lyapunov exponent. So interest in this, as I will mention briefly, is due to some connections to gravity, and of course, works by now famous works by Stanford, Moldasena, Kitaev, and what Steve talked about Tuesday. But also, it's kind of nice object if you just want to calculate something, I guess. So because they can be calculated in also for many body systems, and it's a pretty straightforward quantity to calculate. Now, of course, it all makes sense, these definitions, if they're, oh, sorry, yeah. And I should mention again, so that this, has been studied also in the context of high energy physics. So, and perhaps the most interesting class of result was due to Kitaev, Moldasena, and Stanford, who considered a certain, actually, out of time ordered correlator in the context of many body systems, and have proven under certain assumptions that there is a bound on this Lyapunov exponent, and it has been very interesting research. So in particular, quite remarkably, so this bound was shown to saturate for a certain strongly correlated model such as SYK4 model, Subir's model, Sajiv-Kitaev model, which have interesting dual descriptions. And in some sense, you can think about this dual description as mapping this many-body model on a negative curvature manifolds, manifold where you have basically trajectories that diverge, just classical motion, which diverge because it's negative curvature manifolds if you go on geodesics, and that's actually your Lyapunov exponent, how, depending on how fast you go, which scales with t. Okay, so now, of course, I said, well, there are three definitions, but it makes sense. I'm going to go now to simple systems for now. So I'm not going to talk about gravity. Don't know anything about that. So, but I'm going to talk about just briefly about, well, are these definitions actually consistent? So there are three approaches to quantum chaos, if you want. And well, BGS conjecture kind of says that, yeah, if you quantize something chaotic, you better get Wigner-Dyson. So in some cases, as I said, in most cases, it is actually the case. So for instance, if you do quantize the Bunimovich billiard, this basically stadium billiard, you will get Wigner-Dyson. You can also calculate the out-of-time ordered correlator, which we did in one of our papers. So in here, what's shown is basically this correlator as a function of time. And it actually, for a specific initial condition though, for this initial condition where you launch a minimal uncertainty wave packet and just bounces off of the walls, and eventually, well, this is actually developed quantum chaos. So what you see here, actually, if I run it again, so this is just first hit at the wall, and this time called Ehrenfest time is when your wave packet has spread to the length scales of your system. This is where classical physics is gone. And you no longer have exponential growth. So this stuff is exponential growth. So in this case, the definitions are consistent, but in other cases, it is not necessarily true. So, and I'll just mention in passing our work with actually Bunimovich. So by the way, I mean, it's kind of a funny story. So I was giving a talk at a chaos conference, and I'd been under the impression that Bunimovich is a 19th century mathematician, but he was actually sitting in the first row and asking questions. I didn't know about that. It was quite a surprise, but we started collaborating. And so this is one of the papers we wrote where we showed that, this out-of-time ordered correlator can sometimes move basically within these chaotic hierarchies. And it's not actually, even in the simplest cases, it's not in fact a good diagnostic of chaos. So what's plotted here is, I'm not going to talk about it, it's not really crucial, but what's plotted here is a certain billiard, a polygonal billiard, and it has been proven mathematically exactly, it's a theorem, that Lyapunov exponent for polygons is always 0. But if you put a finite size particle or a wave packet in such a system, in some sense it rounds off the corners and promotes the system into a chaotic system. So in this example, you have kind of quantum mechanics giving rise to exponential growth in a non-chaotic system. But you can also find plenty of examples, such as, for instance, here, where people just studied stadium billiard with the wrong quote unquote initial condition, just ground state, thermal or some thermal state, and so absolutely nothing. Kind of I'm basically demolishing here. So this approach to OTOC, which is, to quantum chaos, I'm saying, well, basically maybe it's not a great definition if you want. And in particular, in the many-body case, in many chaotic systems, such as spin-1/2 chains, they don't really have classical analogs at all, and you will never see exponential growth, and you would think that you don't have chaos, but in fact you do. So it's still an interesting object, though, but let me not talk about it anymore. So let me just now jump to the main subject of my talk, which is basically kind of going back to the old way of describing quantum chaos through level statistics. And here I'm going to spend, again, as a part of extended introduction, a few minutes reminding you what that is. So basically some basics of random matrix theory. So essentially, let's just go to the simplest sort of example, which is the unitary ensemble of random n by n matrices distributed as so in a Gaussian way. So this is a Gaussian unitary ensemble. So, and the so-called Haar measure is simply a product of all independent matrix elements, the real diagonals and off-diagonal complex conjugate elements. That's it. So what we're actually interested in is the distribution of eigenvalues. We don't really want all this information. And of course, you can diagonalize the Hermitian matrix by unitary transformation. And if you do so, you will get this Haar measure, which will include a Jacobian and basically all these angles that diagonalize your matrix, which you don't really care about all that much. And the only thing you care about are the actual eigenvalues. So the goal here is basically to integrate them out, get rid of them. And you can immediately see level repulsion just from an example of, let's say, if you do have, what is level repulsion? You can't have two levels the same. Well, if you do have two levels the same, you have basically a unit matrix that you're diagonalizing. So in any unitary transformation will just collapse, of course. Nothing will depend on these angles. And Jacobian, which is derivative of it, is 0. So that's going to lead to a 0 here. So this is level repulsion. And with a few other reasonable assumptions, such as scaling of this Jacobian and symmetry of the eigenvalues, you end up with this standard canonical and universal Wigner-Dyson level statistics, which is distribution of n eigenvalues. So one thing that I will need is the following. So one can represent identically this level repulsion, the difference between the two eigenvalues, as a determinant, van der Waals determinant. And using pretty standard linear algebra, one can also show, which is just by adding columns and things like that, that in fact, you don't really need van der Waals determinant. You can have any polynomial of degree I minus 1 in these entries. And this will, again, reproduce the level repulsion. So it doesn't matter. So the question of what polynomial to use then becomes a question of convenience. And since we have exponential here, well, the convenient choice is Hermite polynomials. So then the convenient way actually to write the, for calculations, to write the Wigner-Dyson level statistics is just by writing it essentially as a fermionic Slater determinant. So it, should remind you, of course, of harmonic oscillator wave functions. And that's exactly the reason why it's convenient, because you can integrate these orthogonal polynomials with these exponentials and calculations are nice. But in principle, you could have used any other polynomial if you wanted to. So now this, distribution function has still too much information in some sense. I don't really care about, I don't know, 10 to the 23 levels in the many-body system, for instance. So, so one thing we can do, we can trace out, some of them and leave M, and this will lead to correlation functions, M-level correlation functions. So the simplest one is M equals 1, which means that you trace out N minus 1 energies, and you are left with this density of states, which is called Wigner's semicircle law, and it looks as so. So another one, which is actually the key, and it took me a while to get to it, which is something I will study, is the two-level correlator. Basically, when you trace out, you care about how two levels are distributed, and there is no exact expression, but in the large N limit, you get this result, which actually Steve also showed, basically just gave it in his lecture on Tuesday. And so it looks like this. And so the level repulsion is really this sign term, which eventually, suppresses the two levels being close to one another. So just a little bit of a funny, not a funny, curious thing. So a numerical experiment shows that this R2 also appears as a correlation function of the imaginary part of the non-trivial zeros of the Riemann zeta function. It's called Montgomery pair correlation conjecture. Well, it's conjecture because nobody knows why it is so, but it is numerically kind of a fact. So that actually these zeros, which of course are related to a very important mathematical problem, are distributed as per this R2 distribution function, although it's irrelevant to me. So now, finally, I get to the point, kind of, to the object of my talk, of interest in my talk, which is the basically a Fourier transform of this R2. So R2 is a function of two energies. I can Fourier transform with respect to that, or I can calculate the Fourier transform directly, and it will be defined essentially as the average ensemble averaging of two partition functions, sort of, well, complex time partition functions. So this is called spectral form factor. It has, again, I'm just describing standard level statistics. So this spectral form factor has two trivial limits. So if you just set t to 0, you reproduce the size of your matrix squared. If you set t to infinity, you reproduce n. It's called the plateau. When people refer to plateau in various discussions, that's what it actually means. And the physics here, I think, is very trivial, actually. So is that, if you have a matrix and you get to very large times or very small level spacings, there's just nothing there. It's such level spacing. So, and that's why, well, you have basically a constant. So a little less trivial, but still a simple regime is a drop. So, so if you have many levels and squared levels, and then you need to get to a plateau somehow, well, you definitely must fall off a cliff in a sense. And this initial fall of a cliff is easier to compute. It's this slope function, which is also straightforward. But the most interesting stuff happens kind of in the middle, and it includes level repulsion. So, so here comes the thing which is called a ramp, and this is really, again, so for those of you who are not working necessarily on random matrix theory, so this you may have heard about it, but probably don't know exactly where it comes from. Essentially, this is just a Fourier. So basically, we have this function, so this k of t. It's a Fourier transform of the two-level correlation function. And so here, for instance, it's an exact, well, it's a numerical exercise, and you can, in this paper, and you can immediately see what is the, for instance, size of the matrix. In this case, is 100, because, at t equals 0, you see, you have 10,000, and large t, you have 100. But there is a lot of stuff in the middle. And you can kind of see here a linear ramp, linear behavior of this correlator. And where it comes from is simply a Fourier transform of the sine function. If you Fourier transform it, you get the linear thing and the theta function, which is exactly what is called a ramp. So this is the hallmark of Wigner-Dyson. So in practice, when we calculate something and we want to prove that it's Wigner-Dyson, you want to see this ramp. That's what you want to see. If you see something else, it means they have different statistics. So I should say that there have been a lot of work, on deriving the fact that, for example, certain condensed matter models are actually chaotic. So the first, perhaps, well-known paper is, well, Schuller and Shklovsky back in '86, who used just good old diagrams to do so for a disordered metal, just non-interacting disordered metal. And also later, Kamenev and Atlant used Kelder-Sigma model to do it for disordered metal and for just a regular random matrix theory. And this is basically they were just rederiving what we already know using these methods. But the key insight, really, if there is any take-home message here, the key insight here is that in deriving that, if you just actually read these papers, you will see that so this result, in the case of disordered metal, hinges on singularities associated with the so-called diffusion modes. So these modes are essentially the Green's function, inverse Green's function of the diffusion equation, which of course makes sense in the disordered metal. But also what I want to emphasize is that random matrix theory results that we can now call complex SYK2, actually it doesn't matter if it's complex or Majorana, there is just factors of 2 here and there, it doesn't matter at all. But if you just have a Gaussian model like this, so all the results can be just read off by taking 0 Q limit of this model. In fact, that's kind of one of the points of their papers. And in a sense, the soft modes in this SYK2 model are basically just 1 over omega kind of echoes of the diffusion.
Can I make some comments here, Victor?
Yes.
So,
I'm sorry, I just.
that's a severe. Yes. Hi. So when people are studying SYK4, they're really looking at correlation functions of the many body levels.
Yeah, of course.
And there's another problem which is very interesting, and as far as I know, not very well solved. Maybe this is what you're working on, which is what are the correlations of SYK2 as a many body system?
That's exactly.
That is not what Altshuler et al. Worked on. They just took the single particle energy levels.
It's our paper. It's what I.
Oh, that's your paper. Oh, okay, excellent. Oh my gosh, oh, wonderful. I will have to read that. Thank you.
Right. So yeah. So thanks, Subir. Yeah, exactly. So actually, so then indeed, so this is Subir's comment is my next slide. So, but that both Altshuler, Shklovsky, and Atlant Kamenev actually, integrable models, and they're kind of single particle chaotics. If you want, it's a many body system that you poured in a classical chaotic background, but there is no quantum chaos, quantum many body chaos there. So what's of interest is to calculate, as you just said, many body level statistics of this model. And I actually was silly enough to give it as an exercise just to look it up to my poor student, Amit Vikram. But it turned out that it hadn't actually been done. I was shocked that there was no kind of textbook result on that. So anyway, so what I'm talking about here is that, when I was talking about the Wigner-Dyson level statistics that Altshuler, Shklovsky, and Kamenev et al. Have derived, of course, this is just still single particle level statistics. So it's single particle physics. But for instance, if we actually want to populate fermions into a Wigner-Dyson matrix, so fill them up to a certain Fermi level, chemical potential, well, it's totally different ballgame. Well, and totally different energy scales involved. So, and this is exactly what we first did. So this is our first paper on this, so which is many body level statistics of single particle quantum chaos. And most of the work, I should say, was done by Yungshan Liao, who is a Simon's postdoc, and Amit Vikram, who is my student. So I'm not going to bother you too much with the algebra, although this is a lot of algebra. But basically what one can develop here is, well, it's combinatorics in the end of the day, because this is a Gaussian model. You can just use the good old like random matrix theory. So essentially what we're calculating now is the same kind of spectral form factor, but relative to the many body levels, to this capital E, sorry, going back and forth. So this capital E as opposed to the single particle level. So what I'm writing here is that you have single particle levels and you put 0 or 1 fermion on each of them. That's it, that's all I'm writing. And what we know is that these guys are distributed Wigner-Dyson. Now I want to know what these guys do, the many body levels. This is what we're doing. And yeah, one can basically develop rather straightforward calculation, but very well, straightforward but complicated. And I'll just present the result. So what's presented here is spectral form factor for random matrix model / SYK2. So the black curve is a exact numerical calculation, I believe, for n equals 500 or something like that. So so L here is actually the size of the Hilbert space, many body Hilbert space. So it's not n anymore, it's 2 to the n, it's exponential in n. So the challenge here really is that we are now dealing with very small energy scales. And we have been able to find analytic solutions for 3 regimes. So the first one is where you fall off a cliff at small t. Then, well, this is really the part that is interesting. So if you remember in the previous kind of single particle canonical Wigner-Dyson discussion, I was telling you that there is supposed to be this linear ramp in the Wigner-Dyson model. So here instead we see this huge exponential ramp, very fast ramp in time. So, and eventually it does approach a plateau, and it does so very quickly because of this exponential. And basically, well, these are the equations. So we're going to discuss what they mean to the degree possible. So this is obviously not a chaotic model, but it shouldn't surprise you because the model is quadratic and fermions. It cannot possibly thermalize, right? So what I was expecting is just pure Poisson, but I guess the surprise was that it's a bit richer than that. So there's a lot of structure, which kind of still is inherited from the single particle level statistics. So if we kind of, here is the results are presented in logarithmic time scale, right? So we have n, and it changes from 1 to 2n, and n can be very large. So if you look kind of at the big picture in actual linear scale, well, that's what it looks like. So you have, n, 2 to the n, which I can't possibly plot, let's say 2 to the 500, right? Or, okay, maybe in this case it's 2 to the 240 for some reason, but it doesn't really matter. It's a huge number. You drop fast, something is going on you can't really see here, and then it goes back up. And that's a good fit for this going back up to this plateau region. So actually, if you increase n even further, you will see that it's well approximated by simply a theta function with some coefficient here, n being the number of basically fermions. And t, when you think about t, what is t? So t is basically 1 over level spacing that you're considering. You have basically some landscape of level spacings in your many body spectrum, and t pro is kind of Fourier transform of these level spacings. So anyway, so if you now want to go back to this energy picture instead of this fictitious time picture, so all you have to do is just Fourier transform this new ramp. And if you do so, you will find this correlation function, which is actually different from Wigner-Dyson. So, and it's different in part because it shows something which looks like level attraction as well as level repulsion. So basically there is some landscape kind of, again, kind of coming from single particle chaos in the many body spectrum where it's maybe more preferable to have 2 levels at this distance as opposed to some other distance. So if I have this delta R, which is the difference between this thing and essentially what happens at large energy separations. So if you have it negative, you have the kind of expected level repulsion. If you have it positive, you have level attraction, which never happens in the standard GUE statistics. And I don't know what that actually means. So we tried to understand, but I don't understand it. But it might be important potentially because, kind of as a future, potentially something to look into. So because there is this rather famous by now paper by John Imbrie, which is perhaps one of the very few actually exact proofs of many body localization. But right in the abstract, and actually assumption number 1, it's on page 2 of his paper, he assumes no level attraction in some sense, which I don't claim to entirely understand, but here, this level attraction that we find, kind of islands of these level attractions happen, kind of survive. And this is something perhaps to think about. But again, we don't really understand. So now, what I just described is many body level statistics in actually an integrable system, because the system is quadratic. Okay, it doesn't thermalize. It has integrals of motions, which are the single particle energies themselves. So what we want to understand is how to get from this picture, which has no name necessarily. I mean, this is just, it's not Wigner-Dyson, it's not pure Poisson, it's something else. But it should go into just regular Wigner-Dyson. And we know actually what we want to get. So we want to get a result where you have an initially, L squared, which is the size of your Hilbert space. There is some drop, and then there is a linear ramp up to a plateau. That's the result. The result we know. We don't know how to get it necessarily. And unfortunately, the usual random matrix theory approach here doesn't really help very much because, well, interactions, it's not interaction friendly. So we need another approach. And that approach is a field theoretic approach with using sigma models. In fact, it was actually first used by Saad, Schenker, and Stanford. I don't think necessarily even called it sigma model, but actually the approach to SYK model is basically a sigma model. So, but let me explain what I'm doing. So I'm calculating again now this spectral form factor, but now I'm doing it using just Grassmann field theory thing again to start with without interactions. But this is an approach which is generalizable to interacting theories. And so basically, this is my random matrix, and here I have two complex conjugate kind of partition functions, backward and forward evolution, much like in Keldysh formalism. And there is quote unquote Matsubara time. There's no temperature here, by the way, but there is this time that we care about, and it, Fourier of it, of course, is discrete. Anyway, so this is the model, and basically what sigma model does, it averages this theory, which is quadratic theory in terms of H. It's a quadratic Gaussian ensemble, then which generates kind of interaction terms for fermions. And then we decouple them again using Hubbard-Stratonovich field, but we do so in the collective coordinate approach, which is this thing. And eventually, for instance, in the context of disordered metals, this actually leads to diffusion. But here we don't have space, so there is no diffusion. We just have this collective field. And so we get this field theory now written in terms of this collective field. So A and B indices correspond to the backward and forward evolution. It's plus minus 1. So these are just two energies. And so that's it. So that's what it looks like. Not maybe very nice, but what we can do, we can study a saddle point of this action. So it was studied actually in some similar context in the context of replicas, again, for single particle chaos by Kamenev and Mazur years ago. But here we can get sort of a very similar result. So we can find a saddle point of this action, actually saddle points, plural, a lot of saddle points. And essentially then, well, what we can do, we can calculate our spectral form factor as a sum over all these saddles and Gaussian fluctuations around them, which are generated by unitary rotations of the saddles. And so that's what we want. And this, if you just ignore the fluctuations, which you shouldn't, so the saddles would give rise to this initial slope, which is actually not very interesting. But then if you do include the saddles, so there are three types of modes that appear. So massive modes, where basically this is like a propagator of these Qs. Soft modes, which are essentially what used to be Green's function of the diffusion equation, but now it's just 1 over omega, 1 over epsilon. And zero modes, where we are just zero. And one thing which actually Brian Swingle pointed out with his students, I don't know if they're attending here, so and we also found it, is that, well, zero modes are kind of interesting because, well, you can get this exponential growth just from zero modes. If you basically, if you just find values of energy and count them, how many are there? You can convince yourself that the contribution of the zero modes goes as n to the t with some coefficient. So this coefficient, it seems that you do need all other modes to calculate the coefficient, but the actual exponential growth of the ramp, this is the ramp we found in the non-interacting model, you can read off from this behavior, from these zero modes. Now, the last thing I briefly want to mention is, I don't know if there are any questions. So the last thing I want briefly to mention is, of course, this is a non-interacting model. So it's not many body chaotic. So, and of course, it would be very interesting to calculate, to actually prove that a model is many body chaotic. And of course, SYK4 is such a model, but it's perhaps more complicated than the model that we kind of have been studying anyways for a long time, which is basically weakly disordered system, or this SYK2 time system, plus weak interactions. I don't need strong interactions. I don't need random interactions. I just need some interactions to break integrability. So I don't know, we can call it SYK2 plus, for example, if we want. So I don't know exactly the answer. So this is a work in progress, but I think we have kind of an idea of where things come from. So I mentioned to you that kind of all this ramp, this huge ramp that is found comes from zero modes of our theory, which are basically diffusion propagators. You can generalize this theory to interacting models. So, so what is written here is actually a theory for the disordered metal. If you don't like disordered metals, you just set this derivative, just remove this part, and then it becomes SYK2. Right, so and interactions give rise to additional terms that you can also decouple in the Haber-Stratonovich field. And well, it's very technical, so I'm not going to bother you too much with that. But I will just say that this is the kind of model we studied for a long time, because in the context of weak localization and other things in mesoscopic systems, and we do know that one thing that interactions do, they introduce a gap or mass, or whatever you want to call it, to the zero modes, soft modes, to the diffusion modes, essentially. So, and it comes about, you can, it was done almost 40 years ago now. So essentially, what is that you want? So you want to find diffusion propagator. Diffusion propagator is a solution to the Green's function of the diffusion equation. So without interaction, it's just diffusion equation, that's it. With interactions, you get also this stochastic addition to it. It's a stochastic differential equation you got to solve. And if you do so, which they did in 1982, you get essentially a change from this to this. And what it does, it obviously will suppress the exponential ramp to something else. I don't actually know yet if it's going to be linear that we wish to get, but it certainly will suppress the ramp. And that's basically our current follow-up work on the one that I just presented. And what we want to get chaos emerging from interactions, Wigner-Dyson statistics, and this transition sort of from single particle to true many body chaos, which I guess should manifest itself as emergence of an approximately linear ramp at large times. So this is a spectral form factor. So anyways, so I think I'm done, and I'm pretty much, I guess, out of time. So I'll just mention my, I'll acknowledge my discussions with Mark, who I see is here, and the work, of course, of Yongshan Liao and, oh, I'm sorry, Amit, I was just doing cut and paste. So it's Amit Vikram. And also some early work with Leonid Bunimovich, Ram Ganeshan, and Efim Rosenbaum, who unfortunately left physics. But, all right, thank you very much.
Thanks, Victor. We actually do have a couple minutes still till the end of our time. I think that maybe Subir had a question or a comment.
Yeah, thanks, Mike. So in the random matrix model considered as a many-body system without interactions, I mean, the level spacing is 1 over L, right? But you went to the plateau already at a time of order N rather than L.
Yeah, so because
right?
it's not
that's surprising. I mean, that's surprising. Is there a simple way to understand that?
Yeah, I think so, because, well, actually what I was expecting, so let me just get to the result. Sorry, I'll have to.
Yeah, that one.
Yeah, let's, yeah, this one or the other one, right? So, right, so, well, the model we're studying is integrable model, right? So this model, sorry, so this model is, okay, what is the model? The model is a random matrix here and some fermions. Majorana, Dirac, it doesn't matter. So So this model is not it's chaotic in the single particle sense, but it's not chaotic in many body sense. For instance, if you prepare it in some state, it will never thermalize, right?
So naively, I would have expected Poissonian statistics at the scale 1/L. That's what I would have thought.
Yeah, but actually, so basically, I think the way to understand it is that this part is, so there is still some level repulsion at the single particle energy scales. So essentially, if you right, so you have the many body level spacings, which are very, very small. They're tiny. So, but there is still some energy region, right? So where the system seems to remember it came from a classically chaotic system. So I think this is the physics of it. So I think exactly this is, you will get to plateau in the many body chaotic system at 2L. That's at time of order L. That's exactly what I want to get, actually. So if you have a DRAM, this is what would have happened. But this would have implied many body quantum chaos, which it is not. So this is a bit, again, maybe confusing, that the model is chaotic, but not in the many body sense. It's a chaotic in the single particle sense.
Okay, one more quick follow-up question. So if I add a very weak interaction to this model,
yeah,
you expect immediately this plateau at L to just come down to nothing? It just immediately disappears at this time?
Yeah, I expect, okay, I mean, I think this is what is going to happen. So, okay, this is going to happen. So there will be there will be a completely universal picture. So I don't yet know how exactly interactions come into this. So it might include interactions here, but I do believe, yes, so that there will be some system size essentially, which just overwhelm completely all the single particle stuff. So everything I was talking about in the single particle chaos happens at this, it's like a blip here, right? So because so the L is the Hilbert space size, it's 2 to the N, right? So all this single particle stuff happens here.
But you already were at L, even at times of order N there. It wasn't there. It was already at L.
So okay. So the reason I went up here so quickly is because of the exponential ramp.
Oh, I see.
So now, and this ramp I think comes from zero modes, which are, well, in particular, zero mode soft modes, diffusion-like modes, which will get a mass the moment you add interactions.
Okay.
And this will lead to a slower growth, and therefore it will occur at a later time. So that's what I expect. That's what we expect and kind of sort of see, but it's still work in progress. Yeah.
Okay. Good. Thanks, Victor. I think we should probably move on. So thanks for a very nice talk. We're just slightly over time. So rather than cutting out the break completely, what I think we should do is just shorten the break to a 5-minute break, and